Out there, do you? I was doing the countdown 5, 4, and I think when I got to 1, the wrong finger was up. But that's how it goes. Hey, welcome everybody. How we doing? John Barba, along with Jason Cox and Dave Holdor from the Takeo Training Department, and we welcome you to yet another edition of Takeo Tuesday. Hope everybody's doing well. We're so happy to have everybody here. James Zampano's already chimed in. That's awesome. Welcome. This is going to be a fun one. We're going to be talking about a topic that's near and dear to my heart and has been for a long time. And we're going to be talking about sizing, piping, and pumping for indirect water heaters. All too often, you guys know this. What size pipe is almost always used to, for the boiler loop to an indirect water heater? You guys know this, right? 99 times out of 99, what size is it?
It's 3/4 all day. Quarter.
3/4 inch copper all day, every day, because that's the size of the tapping. Why screw around? And what circulator does it get? Usually a 007 or equivalent, right? Not always correct, not always the best way to optimize the performance of that tank. But the thing is, we almost always get away with it, and it's quote unquote good enough. Not optimal, but good enough. Hey, if they run out of hot water with an indirect, they're probably just doing something weird. Okay, that's kind of the approach. But we can do better than that. Okay, if we understand what the specs tell us, if we understand piping and understand pumping, we can do better than that. And Dave, you look like you want to add something. I keep, every time I look at you, you're opening your mouth, going towards the microphone. What do you want to add, bud?
Well, yeah, I look at this thing too. What's our homeowners' expectations when it comes to hot water or to DHW in the house?
That it's hot and it gets there. Yeah, it's their expectation is high, I would think.
It's low.
No, I expect they.
Right.
Okay, I'm thinking they want a lot of hot water and they don't want to run out.
Oh, they do, but they do run out and do nothing about it.
There you go. Okay.
So
I
yes,
agree. Okay, good point.
But the reality is that it's low. People run out of hot water, and I look at this topic too as a. If you're in somebody's house, take a look at this. Now, you might be there for other reasons because they did not call you because they don't have enough hot water. You're there for some other reason. So take a look around, especially here, and ask those questions. Now, you may not get that work that day because you're already there in the house for other reasons. There's already a bill going across the table, all right? But let them know that this is available, all right? Take a look around and ask them these questions, and as we go through the presentation, you'll see most of this is not intended by the installer. These are somewhat self-inflicted wounds that compound each other on top of each other, and gets us into this situation. So that's why I like to talk about this as well, because we can now turn into a hero for a customer. Because again, most of the time they don't want to see us, but now you give them options and say, I can get you all the hot water you want, really.
There you go.
I'm going to add one more story. And so my house here, all right, my house here we put an addition on for my in-laws, and my in-laws moved in. And when they moved in, inevitably, my mother-in-law would come over to my house once every other day and make an announcement through the connection. And that announcement was, I'm doing the laundry. What is that code for?
That she's lonely. That she's lonely.
Yeah.
Oh, no, that she's
doing laundry. Nobody take a shower, because that's standard, right? Because a washing machine takes a lot of gallons per minute. So that was code. And I turned to her one day and I said, did you notice that we don't tell you when we're doing laundry at our place? And she just thought I was being rude and inconsiderate. And
good bet. Yeah.
And I told her, I said, we don't have to worry about that. I've designed our system so we don't run into that. She had it before with a standalone gas water heater, all right, that was undersized for the house, that it was normal. So that's why I also really like this presentation as well. So I will pass it along back, JB.
All righty. Well, let's get to it. Real quick, if you guys out there in webinar land can just go to your chat question section and do the standard thing. Just say hi, hello, how are you? And let us know where you're from, where you're chiming in from. So we know that you can hear us, number one, and we know that you know how to ask questions, number two. And the other thing I'd like you...
the furthest away too.
Yeah, that's fine. Who's the farthest away or furthest away? Who's away the mostest? Uh, and also, we'd like to just encourage you guys, ask questions as we go through this presentation. Ask questions. We'll take a break every few slides and address a couple questions here and there. There's no such thing as a dumb question or a bad question. There are all good questions. We have dumb answers. We're good at that, but there's no such thing as a dumb question. So please feel free to ask whatever's on your mind regarding this topic, and we'll stay on as long as you guys want to answer those questions. So without any further ado, let us get started on our presentation. So again, today's topic is sizing, piping, and pumping for indirect water heaters. And this presentation it's an older presentation, but it really does illustrate some points. And I'm going to tell a story here now. This goes back to 1995. And my first month at Worsbo Company out in Minnesota. We had a purchasing agent, a really nice guy, who's building his own house. And being a purchasing agent, one of the things that you get to do as a purchasing agent is you get to collect favors. And that's kind of what he was doing when he was building his own house. And he kept telling us about all the deals that he had. One deal that he got was for a two-person jetted tub, like you see here. And he was very, very excited about that. And he really couldn't wait to build the house so he could use that tub for its intended purpose. The other thing he told me was that he got this really great deal. For free, he was given a 40-gallon gas water heater. And looking at this tub and looking at that water heater, I had to say to him, well, what do you intend to do with it? Because you can use it to heat hot water, but if you use that to heat your hot water, the tub is useless. If you want to use the tub, that 40-gallon water heater is useless. What are you going to do? You can't fill it up. You don't have the capacity. You don't have the recovery. You don't have the BTUs. It just ain't going to work. And he looked at me like I was a moron. I'm very familiar with that look. I get it from Dave and Jason a lot. All right. He looked at me like I didn't know what the heck I was talking about. And he says, no, it's a water heater. It'll fill up the tub. He says, no, you just don't have enough. It's a math problem. And he says, well, I'm not going to use it very often, maybe just once a month. So I think he was trying to make a deal with the water heater. If I don't tax you too hard, very often, you can come through for me once a month, right? I said, no, it doesn't work that way. It doesn't. It's a water heater. It's not it doesn't get up for the big game. Okay, it's just a water heater. It's not going to do what you want it to do. So I had to put it in terms that he could understand. If this was him or his wife trying to use the water heater, trying to use the Whirlpool tub with that 40-gallon water heater, this was going to be him. He's going to be taking a lot of cold baths and showers and jumping into cold tubs. That's just the way it's going to be. All right. He had a problem, and it was a math problem. All right. He was a math problem. He didn't have enough storage in that 40-gallon tank for a dump load to fill that two-person tub, nor did he have enough recovery to continue, for continuous use. It's simply, two goes into two doesn't go into five even. It just wasn't going to work for him. The math was against him from the get-go. So we convinced him ultimately that an indirect that was sized appropriately was going to work for him. All right. So what we're going to learn today, what the main points I want you to take home here are, we're going to learn how to interpret the data that is in the spec sheets for indirect water heaters. We're going to look at one particular company, but there are a lot of different data points there that you can look at. We're going to learn to use that data to size the pipe from the boiler to the heat exchanger and back again properly, and how to use the flow demand and the pipe sizing to figure out the head loss so you can size the pump properly. Okay, it's not always 3/4 inch in a 007. If you do 3/4 inch in a 007, you'll probably get away with it a lot, but not all the time. You're going to run into limitations. So we'll discuss all of that. And we're going to look at a couple of options that might help you maximize or optimize the performance of that indirect and get everything you can out of it and get everything that the customer paid for out of that tank. So there's enough hot water. So we're going to look at some options as well. Let's take a look at some spec sheets here. This is from Superstore. Okay, their particular model, or not the Ultra model. It's not that we're recommending them. It's just this is what we have up on the screen. And for the Ultra, you've got two charts. Okay, there's two charts that they give you. They give you the model okay, that give you the capacity. That upper chart's a nice, happy chart. They give you the capacity of the tank. They give you the heat exchanger surface area, and most importantly, the recommended flow rate through that heat exchanger. It gives you the pressure drop in feet of head through that heat exchanger. Okay, flow rate, head loss. Those are two big things for circulator selection, are they not? Okay, so it's the pressure drop through the heat exchanger at the given flow rate shown here. And then we get our first hour ratings, first hour ratings with 180-degree boiler water and first hour ratings with 200-degree boiler water at different storage temperatures, 140 and 115. And it just tells you how many gallons of hot water you'll get over that first hour. Okay, so a lot of good specs there. So let's take a look at that top chart, because the top chart's the happy chart. The top chart doesn't challenge you. The top chart thinks you're handsome, good looking, intelligent, and well spoken. Okay, the top chart loves you. The top chart absolutely loves you. If we look at that SSU 45, that's telling us we have 45 gallons on hand. That's a 45-gallon tank, 20 square feet worth of surface area for the heat exchanger. All right. If we jump way over to that 180-degree boiler water first hour ratings column, we see that we have, if we store at 140 degrees, we have 212 gallons on hand for that first hour. That's the first hour rating. So that's what you have in the tank plus what we can recover. If we store it at a lower temperature, not recommended, but if it were stored at a lower temperature, we could get up to 292 gallons over that first hour. So you look at that and say, oh God, what's not to like? All right, this thing will do anything. This thing's perfect for what we need. 212 gallons. That's a lot of freaking hot water. I like that. I like that. All right. The second chart, the bottom chart's going to hold you accountable. Okay, that's the one that's going to hold you accountable. Now we're looking at that SS45 again. All right, the first several columns there are just dimensional things and working pressure things, shipping weight, connections, all that basic stuff. We got to go all the way to the right-hand side and see that in order to get that output, those first hour ratings, we have to have a specific size boiler. So if we want 212 first hour gallons, we must have 141,000 BTU boiler. If we want the 200-degree boiler water output, we have to have 161,000 BTUs. That's recovery based. Recovery is based upon the BTUs available at your burner. So in order to get that first hour rating, like we said, I need 141,000 BTU boiler to make that work. All right, that's the important part. It holds you accountable. We'll get that 212 gallons with 141,000 BTU boiler. Simple as that. All right, what's the math behind that? Where does that come from? What's the math? Well, the math is pretty simple. All right, the math is pretty simple. First, you look at the water heater itself. The water heater itself, because of just the way they work, when you take hot water out, you put cold water back in. And because we have a coil with so many square feet, I think it was 20 square feet of surface area in that tank, what that tells us is about 75% of that tank capacity is actually usable at the water temperature we're talking about. All right, 75% is usable. So again, the coil space and the cold water, that's why we don't have 45 gallons available. We'll have 75% of 45 gallons available for a dump, and that's going to be about 34 gallons. So in that 45-gallon tank, I got 34 gallons right there for a dump load. That's all I got. Okay, more or less. Again, it may be a few gallons here, a few gallons there, but 75% is a pretty good number. Okay, that's half of the equation. The other half of the equation is recovery, and this is where the BTUs come in. We can only recover, an indirect can only recover based upon how many BTUs that the burner can make, okay, that the boiler can make in this case. So it's all about BTUs and GPM. It's not about like we're figuring flow rates and stuff. We're just figuring what can this indirect water heater do with the BTUs I have available? How much can we recover? And that's just standard math. Okay, that's standard math. And the math is this. The boiler output, in this case, 141,000 BTUs, that's the DOE output, the DOE output, divided by the product of 8.33 times 60 times 90. Now, where does that come from? What do those numbers mean? Anybody out there have any guesses? Where does how does 8.33 figure into this? If you know it, type it in, man. Where does 8.33 come from? What do we mean by 60? And what do we mean by 90? Okay, if you have an idea, type it in. I'd be interested to see where we're at. But that's the formula. Boiler output divided by 8.33 times 60 times 90, and there's an asterisk with the 90. All right. Well, let's take a look, because there we go. We got a couple here. Weight of the water. Yep, Robert Kaplan's got it. 8.33 pounds. 1 gallon of water. 1 gallon of water weighs 8.33 pounds. All right. 60. It's the number of minutes in an hour. All right. That's the number of minutes in an hour. And then 90. What's the 90 stand for? Well, the 90 is the DOE recommended temperature rise. It's just a standard that we use, the temperature rise. We're looking in this case that the water comes out of the ground at 50 degrees and we're storing it at 140. So that's a 90-degree temperature rise. If you're in Alaska, or I see we got Edmonton showing it, the water might be coming out of the ground in the middle of winter a little colder than that. You got to know what that temperature is, and then you can adjust that number as needed. But 90 is what the Department of Energy says is a standard for continental US. Alaska is going to be different. Maybe up in northern Canada, it's going to be different as well. That's going to be dependent upon where you are. All right. So if I were to multiply 8.33 times 60 times 90, I'm going to come up with 44,000 and change. We're going to round up and call it 45,000. So you want to figure recovery. It's based upon the BTUs available. The potential recovery is simply going to be that DOE boiler output divided by 45,000. All right, divided by 45,000. So that's how you're going to figure out your rate of recovery. So let's do a little math, and we'll see where that 212 gallon first hour rating comes from. So if I have 141,000 BTU boiler, I'm going to divide it by 8.33 times 60 times 90, or 45,000. So 141,000 divided by 45,000 gives me a rate of recovery of 3.13 gallons per minute. 3.13. That's what I can recover. That's what this thing can do in conjunction with the indirect. I'm going to round down and call it 3. All right, I'm going to round down and call it 3. So I can recover at a rate of 3 gallons a minute. I have 60 minutes in an hour. So over that first hour, I can recover 180 gallons. Actually, for every hour, I can recover 180 gallons, okay, at a rate of 3 gallons a minute. I can do that all day long. I can do that all day long. Now, 180 gallons worth of recovery plus my 34 gallons of stored capacity, of usable capacity in the tank, if I add those together, well, Glorioski, Captain Kilowatt, look what I have. 34 gallons plus 180 gallons recovered. That's 214. The chart said the first hour rating was 212. Yeah, that's just a little bit of math differential. That's where that number comes from. That's how we achieve that. It's the stored capacity plus the recovery. All right. So I can do 214 gallons that first hour if I just turn the spigot on at 140 degrees and let it run. Okay. I can get 214 gallons, and at a specific flow rate, I can get 214 gallons that first hour. After that, it's 180 gallons. All right. At about, going to be about 3 gallons a minute worth of flow. All right. And that's at 140 degrees. So there's a couple of asterisks there as well. So 214 divided by 60, 214 first hour gallons divided by 60 minutes in that first hour, I can turn that tap on to 3.5 gallons a minute, and I won't run out of hot water. All right, I won't run out of hot water. But there's a big if, right? That's in theory. And Yogi Berra once said, and this is one of my favorite quotes from Chairman Yogi. Yogi Berra once said, in theory, there's no difference between theory and reality. But in reality, there is. Okay, so there is a difference between theory and reality. When reality comes into play, we have to be cognizant of things like piping and pumping. Okay, there are conditions. I need that 141,000 BTU boiler. If I don't have that, I don't have this. Okay. Additionally, I've got to size that boiler piping properly according to the specs. That was 10 gallons a minute, right? And I have to make sure I overcome the head loss, 7.9 feet ahead through the heat exchanger, plus all my supply and return piping. That all has to be included. And then I have to pick the right circulator to do that job. Okay, it's not always a 007 or a 0015 3-speed or a 1558 or whatever. There may be some differences there. So as we go into this, I just want to show you what happens if okay, I'm not putting 141,000 BTU boiler in. I'm sizing the boiler for the BTU load of the house. All right, I'm not sizing it for the indirect. I'm sizing it for the house. How does that affect this? Because if I wanted to get that domestic hot water output, I would need to put 141,000 BTU boiler in. I say, I don't want to do that. Or for whatever reason, I can't because it's not what's there. Maybe I'm adding an indirect, and this is what I'm dealing with. This is the hand I've been dealt. So if I have a smaller boiler, what can I do? What can I do? All right. Well, what's the net boiler output? What's the DOE output? Net boiler output divided by 45,000. That's going to tell me my rate of recovery. All right. So let's say that boiler has a DOE output at high fire of 75,000 BTUs. What can I do now? 75,000 BTUs divided by 45,000 is going to give me a rate of recovery of 1.67 gallons per minute. That's less, okay? That's a lot less than what we had before. So 1.67 gallons per minute worth of recovery times that 60 minutes, now I'm down to 100 gallons of first hour recovery, plus the 34 gallons I was dealing with, plus my 34 gallons of stored capacity. That's going to give me 134 first hour gallons. 134 first hour gallons divided by 60, I'm at about 2.25 gallons per minute for that first hour. So I turn that tap on at 2.25 gallons per minute. I'll get a steady stream of 140-degree water out of that tap for that first hour. After that first hour, I got to turn it down to 1.6 gallons a minute. All right, of 140-degree water. So now we're thinking about 140-degree water here. What are we doing at the tap, generally speaking, whether it's the bathtub or the kitchen sink? We're not taking a bath in 140-degree water. Jason, I know you don't take it. Well, I presume you don't take a bath in 140-degree water.
I haven't taken a bath since I was 8 years old.
I know, and we need to talk. We've been meaning to talk to you about that. Yes, that you have mixing valves. You're tempering at the fixture as well. So that all that tempering does is it extends the capacity. So can we get away with this? Many cases you probably could. The math works in your favor. Some cases you can. If it's one of those houses where they put in a 6-person shower stall, okay, with all these jets going in every which direction to get you clean everywhere, okay, that's going to be a problem. You're going to be running out of hot water mid-shower, and you're going to have six angry people on your hands. That's just the way it works. So what do we do? How do we make what are our challenges here? In this case, most cases, we should be okay. We just have to make sure we do a few things correctly. Let's go to pipe sizing. First off, let's go with this. Say I had the 141,000 BTU boiler, okay? My recommended flow rate is 10 gallons per minute. At 10 gallons per minute, what size pipe should I have? Well, that should be 1-inch pipe, at least, maybe 1.25 inches if it's a long run. But I think we could do 1-inch pipe there, 1-inch type M copper. That should be fine. That should be fine for 10 gallons a minute. My head loss just through the heat exchanger is 7.9 feet ahead. I have to add in the additional head loss for my supply and return piping, which, depending on how long it is, could be another couple feet. Let's say we get up to 12 feet ahead, or not. Let's say it's 10. Let's say it's 10.5 feet ahead. We add additional head. Let's say it comes up to 10 gallons per minute, 10.5 feet ahead. That's the circulator we're going to be looking for. So that's part of the deal. However, that's if we're using that 141,000 BTU boiler. All right. If we're using the 75,000 BTU boiler, we can flow 10 gallons a minute all we want. We're not going to get anything out of it because we only have 75,000 BTUs. We can find out the flow rate that we would need by using our old friend, the universal hydronics formula, which says GPM equals BTUH divided by delta T times 500. All right. So 75,000, that's the BTUs I have available. So I got to figure out my flow rate for that heat exchanger. Here's a tip about the indirect heat exchangers. Most residential hydronics we design to a 20-degree delta T. Some radiant will design to a 10. But with An indirect, we'll typically design to a 30-degree delta T. So the water may go out at 180, come back at 150, average water temperature is 165. That's how that works. So we're going to deal with a 30-degree delta T. 30 times 500 is 15,000. 75,000 divided by 15,000, that's 5 gallons a minute. At 5 gallons a minute, the pressure loss through that heat exchanger is 2 feet ahead. So now you can see how we can make this thing work with 5 gallons a minute. Okay, 3/4 inch copper is just fine. 5 gallons a minute at 2 feet ahead, we're within the realm of a 007. So in this case, we're going to be fine. That'll work just fine. If we wanted that higher output though, we'd be dealing with 10 gallons a minute at, let's say, 10.5 feet ahead. What does that look like on a pump performance curve chart? We'll take a look at that in a minute. So 5 gallons a minute, that's 3/4 inch pipe. 10 gallons a minute is 1 inch pipe. 5 gallons is 3/4 inch pipe. 10 gallons is 1 inch pipe. If we keep that tank close with minimal piping and minimal fittings, we'll keep the overall head loss of that loop down. So we'll be able to find the circulator that's going to work for us. So let's take a look. Here's our example. Let's say our supply and return piping is 40 feet, 20 feet from the boiler to the indirect, 20 feet back. Say I got 1690s at 2.5 feet of equivalent length pressure drop. That adds 40 feet to the overall length, a couple of T's, etc. So that's 80 feet of total equivalent length pipe. To estimate the head loss, I'm going to multiply that by 0.04, which is 4 feet of head loss for every 100 feet of straight, properly sized pipe. So 80 times 0.04 gives me an additional 3.2 feet ahead. All right. So at 2 feet ahead plus 3.2, I'm about 5 feet ahead, a little over 5 feet ahead at that 5 gallon a minute run. At 10 gallons a minute, I'm going to be at a little over 11 feet ahead. So it depends on my boiler size, where I'm going with this here. So let's take a look. Let's take a look at the 0015 standard efficiency. If I was looking at my 141,000 BTU boiler, I would need to have this thing running at high speed. All right, if I had 1 inch pipe and 141,000 BTUs, that's 10 gallons a minute, and we're looking at almost 11 feet ahead. I'd need this thing running at full speed. That would be contractor no callback mode, turn it up high, and that'll work. That would work. If I was doing it the other way, all right, with 3/4 inch pipe, I don't want to have that thing at high speed. I don't want to bring my delta T down because I'll short cycle the boiler. I want that thing running at low speed, giving it the 5 gallons a minute that it requires, and not twice as much, because I'm not going to get, if I cram 10 gallons a minute through that, I'm not going to get more output out of that tank. I don't have the BTUs available. All I'm going to do is cut the delta T in half. It's going to be 15 instead of 30, and I'm going to short cycle, baby, and we don't want that. Okay, at 5 gallons a minute with a 75,000 BTU boiler, I set this pump to low, it's going to work just fine. The circulator will be running at low speed, it'll be working just fine, and I will reduce the likelihood of short cycling. Does that make sense? Does that help us? All right, Dave, do we have any questions out there that we need to address? But does this make sense, and is this something that you guys think you can apply out there in the real world?
So we don't have any questions at the moment, but I think, we got people posting in there still on where they came from. They're trying to find who's the furthest away. I didn't say from where.
Okay. Yeah, that's true.
I'm just messing, of course. But no, we don't have any questions. But John Jackson did have a statement there. He was saying, back in the day, before I understood how to size the systems, he's got his heating system in his house. He designed it. It was a big project, had snow melt as well. And it's been running 10 years great. So yeah, you had more than enough design for hot water because of the large heating system that he had, and with the addition of the snow melt thrown on there too, probably. So that boiler was probably sized well enough, if I'm reading that correctly. Yep. Oh, 35 by 18 snow melt. Yeah. So yeah, he had a pretty good sized snow melt, so that tacked on some size for his boiler sizing, which is going to help you get that indirect tank to run where you expected it to be. So awesome.
There's a common question we always get is, should I size the boiler for the heating load or should it be sized for the domestic load? And I think that's a really good question. Personally, I'm a little counter here. I say size it for the heating load because you can do things with the tank to make up for that. Bigger tank, more storage, all right, is one thing. Store at a higher water temperature, which we're going to discuss in a little bit, tempered down, that'll help you as well. So it's, what did my cousin Vinny say? Good kicking $200. Where are we going to go here? It's like sizing a heat exchanger. Do you want a bigger heat exchanger and a smaller pump, or a smaller heat exchanger and a bigger pump? It's BTUs, man. The boiler's making the BTUs. We got to understand what we're trying to accomplish. So I don't think there's a wrong answer. It's just which direction do you choose to go? Me personally, it's size for the heating load. If the domestic load is bigger, well, let's figure out how we're going to make that work. Okay, because you can't not address it. It's just how you address it is the important part. Okay.
Right. Yep.
So good. All righty. There's a lot of caveats involved here. Okay, a lot of things we have to consider. First off, understand that we're storing at 140 degrees, which buys us capacity. We're mixing valve at the tank is very common and should be, and we also mix at the fixture. So there's a couple of things to take into account there that buys us time, buys us capacity, so to speak. That 90-degree temperature rise, that's the worst case, okay? That's the worst case. You're in Alaska, you got to use a different number. We understand that. But 90-degree temperature rise, meaning the water's coming out at 50 and we're bucking it up to 140, all right? So that's the worst case situation, and your usage is going to vary, okay? That we understand. The usage is going to vary throughout the day, throughout the week, throughout the month, okay? Where you run into trouble, it could be consecutive showers or concurrent showers, all right? Or having a tank that doesn't have enough of a dump capacity and trying to fill up a two-person tub for an evening of candlelight enjoyment. That, that's just math. You got to do it. You got to do what you got to do there. So there's a lot of caveats involved. One of the things that we can do, and we discussed it just a few minutes ago, was you temper at the tank, you extend the capacity of that tank. The stored capacity goes up. If you temper at the tank and temper at the fixture, you kind of double down. Okay, that helps you in both cases. The cool thing about mixing valves at the tank is there's math involved, and we can put a number to this. And anytime we know what we're doing, it gives us a little bit better. It gives us a little bit better a feel and a little bit more control. So a tempering valve helps. And that picture you're looking at, that goes back to, Dave, this is the original one from 1927, is it not?
I believe so, yeah. Yep.
Yeah.
This is one of our first ones, correct.
Yeah. That was one of our very first ones. Taco, as you know, is a 105-year-old company. Our first product was, ironically, a precursor of an indirect water heater. We had a copper coil and a cast iron casing that was a sidearm water heater. In this case, the domestic water went through the copper coil. The boiler water was in the cast iron casing. So it was a reverse of what we think of with an indirect today, but it made a metric crap ton of really, really hot water. So hot, in fact, that it led to the development of our second product, which was the mixing valve, so we could bring that water temperature down a little bit. And that first one came out in 1927. So the tempering valve helps because it makes the tank think it's bigger, all right? It makes the tank think it's bigger. And because it's Taco, there's a math formula involved, and I know how much we love math formulas. This is a two-step math formula, okay? This is the first step of the math formula. T mix minus T inc divided by T stored minus T inc equals your storage factor. Now, what the heck do those numbers and letters mean? T mix. T mix is the temperature of the mixed water that leaves the mixing valve. All right, it leaves the tempering valve. That's what we're tempering down to. Minus T inc, that's the incoming cold water. So that's going to be, in our case, 50 degrees. All right, what we're going to try and do here is we'll pick a mixed temperature minus the 50-degree incoming water temperature, divided by the temperature, the T stored, that's the temperature of the water being stored in the tank, minus the temperature of the incoming water. That's going to equal part one of our math formula, the storage factor. All right, the storage factor. So let's do one. We're going to do an example here for you. All right, and we're going to show you how we can create capacity. So let's use 112 as our team mix. Arbitrary, seemingly arbitrary number, but we will discuss why we used 112 in this particular example. 112 minus 50, that's T mix, minus T inc, all right, the incoming temperature, divided by 140, that's the temperature I'm storing at the tank, minus 50 degrees, all right? So 112 minus 50 divided by 140 minus 50. The first thing we do in math is we simplify. All right, 112 minus 50 is 62. 140 minus 50 is 90. 62 divided by 90 gives me a storage factor of 0.69. 0.69. Now, let's take that a step further into part 2 of our math formula to figure out how this mixing valve impacts the stored capacity at the tank. All right, usable capacity of the tank divided by the storage factor that we just figured out, it's going to equal my tempered capacity. Now, the usable capacity we've agreed earlier on was 75% of the actual capacity of the tank. So for this example, we're using that 45-gallon tank. We really have 34 gallons of usable capacity. So 34 gallons divided by 0.69 gives me almost 50 gallons now. So we've increased the stored capacity or the tempered capacity of that tank by almost 50%. All right. So now my dump is nearly 50 gallons instead of 34. Add that to my recovery. I've basically added given myself a 15-gallon buffer here. All right. So that's one way in which we can use a tank, a mixing valve at the tank to boost the capacity. We mix at the fixture as well, either using the faucet or in some cases, if it's a commercial building, a point of use mixing valve, which is very common because they'll run really hot water through the system and then do point of use mixing. Get it? All right. But this in residential applications, you know, we would mix at the fixture with the faucet itself. It's going to give us extended capacity as well. Now, this is step one. We could, if we really ran into a situation where we needed to extend we didn't want to, replacing the boiler wasn't feasible, maybe because it's a new boiler and why do it? And replacing the tank isn't feasible because it's probably fairly new and why do it? But they're not getting enough. No matter what we do, they're not getting enough for their needs. So here's what we do. You can push the old envelope a little bit, right? You can push the envelope. There's nothing says we got to store at 140. There's no rule that says you must store at 140 and not one bit more. We can store at a higher temperature if we wanted to. Does it use more energy? Well, yeah. That's not the point. The point is we're not meeting the hot water needs right now. So we could rip out the boiler, rip out the tank and put in bigger ones. Or we could bite the bullet and say, you know what? We're going to just increase the stored temperature of the fluid and see what happens. So what if we were to store at 160 instead of 140? What does that do for us? Okay, so now 112 minus 50 divided by 160 minus 50. We simplify 62 divided by 110. That changes the storage factor to 0.56. Now 34 gallons divided by 0.56, that's 60 gallons. Now our tempered capacity of the tank is 60 gallons, and that basically is the same usable capacity as an 80-gallon tank. All right, so what we've just done is we've turned a 45-gallon tank into an 80-gallon tank simply by storing at a higher temperature and then mixing at the tank. All right, that's how you can get an underperforming indirect, maybe to closer match the expectations of the customers or the needs of the customers without ripping stuff out, simply adding, storing at a higher temperature and adding a mixing valve at the tank. And then we mix again at the fixture. So that helps us out.
That was
Dave.
That was my exact situation.
Yeah, there you go.
Before we put the apartment on the house, I had a small tank in my house and I had more than enough hot water for the 4 of us. Then we added an apartment, 2 more people, separate shower, separate everything, separate laundry room. So I did do that because my boiler room is a closet. And I also have 6 zones of heating in the house. And if I were to put a 60-gallon or an 80-gallon indirect tank in my closet, I would have stuff on the back walls I'd never see again. I wouldn't be able to get to my manifolds and my circulators and stuff in the back there. So keeping that same tank, that small tank, low tank that I had in there, I just increased the water temperature. I put the mix valve in, increased the water temperature, more than enough hot water.
There you go.
Yeah,
so
well,
that
guys,
situation changes. Also think about adding a mix valve in there. So
guys, what do you also think about critters like Legionella? I think we're happier at the 160 water temp, right?
Oh, that'll take care of anything in the tank. Absolutely. Yeah.
Yeah,
That'll take care of anything. And flushing the piping will certainly help as well. Bigger issues in commercial systems because you got a lot of water that can be stagnant for a long amount of time. So yeah, that higher temperature, that's why they'll have point of use tempering in commercial buildings to take care of Legionella in the piping system.
Right.
So yeah, got a couple questions.
Yeah, it is interesting thinking about Legionella for a second. So I know some stats on this, and
good.
You know, when you've got the water at 130 degrees, all right, you can destroy the Legionella if it happens to get into the water in 5 to 6 hours. But here's what's interesting: in a water heater or in water, Legionella is actually the most ideal growth range is between 95 and 115 degrees. And if you think of your tanks and where we keep the temperature sensors, you know, if they're maybe a third of the way off the ground and you store it at 120, everything below that is ideal growth range, you know, for that Legionella bacteria to get in there. But yes, you can disinfect over 158 degrees. And I'm starting to see a lot of controls, a lot of components being built in, so where you can periodically ramp stuff up to a high temp for that disinfection, bring it back down again. So also we don't have that scald issue as well. So
cool.
I've seen a couple of questions pop up. One was about what kind of efficiency loss would there be by increasing temperature? There'd be some, you know, but again, you're dealing with an indirect hot water tank that's ridiculously super insulated. So your standby losses are minimal anyway.
about a half a degree an hour.
About a half a degree an hour. So if it costs you, it's one of those things, I'm not sure you would notice much in your fuel bill. I think you'd notice if you ran out of it didn't do this and ran out of hot water regularly. This is one of those things you do if the system you have is underperforming and you want to try to improve the performance without ripping stuff apart. Yeah, hey, listen, you store at a higher temperature, yeah, it's going to cost a little bit more, but I don't think it's something that's going to be crippling or even noticeable, really. I think it's going to be a few bucks here or there, but it solves a problem that is very noticeable and rather irritating. So that's the trade-off. It's all a trade-off. You know, it's all going to be a bit of a trade-off. It's just the way it is. Okay. Any benefits to a master mixing valve at the tank than just mixing the picture? Well, yeah, a couple of things. First, anti-scald, because you're not relying on the user to make sure he doesn't burn himself. Okay, that's number one, and it's just very reliable. Okay, it's very reliable, and you kind of double down. You mix there, then you mix at the fixture. Life is good, you know. But scalding is probably the biggest one to do that master mixing. Now, Dave, I know there's a couple other questions, but I wanted you to you explain this way better than I ever have been able to. Why is that 112 degree temperature there unique?
Oh, right. Okay. So that actually jumps back to the slide before your previous example. So that's why we have it adjusted to 112 degrees. So the previous slide where we were not mixing or we're storing at 140 degrees, and we chose the 112 for this example. And usually people jump up and down like, oh my God, 112, that's way too cold. You need to have, you know, come out at 120. Because that's what every mixing valve is set for. It depends on the mix valve and the thermostatic elements that you have inside here. What you've got is you're basically opening and closing the hot side of a mix valve, all right, in order to maintain your temperature on the outlet side. So you've got cold coming in, you've got your hot coming in, but you're limiting that hot side coming into that valve to give you a mixed temperature coming out. And depending upon the valve, there's a lot of different variations to the thermostatic element. They want to see a differential, all right? And there are differentials in valves that are 27 degrees. There are differentials of 10 degrees, and there's some as low as 5 degrees. So what that means is that you want to see a more than the hot to the outlet, to your mix temperature of 27 degrees. That's your minimum that you should be at. You can go more. So in an example like this, if you have your tank stored at 140 degrees, you want that water temperature set for 112. If you want 120, then you want to store at 147. All right, so that's why we start looking at that. And we see those 27-degree spread valves installed often because when you look at a 10-degree valve, they might look the same on the outside, but now you've got a couple of dollars difference. And not knowing the differential in there, that's really what you need to pay attention to, and what you have coming out of the tank and what your desire is going out to the house itself.
You always look at the differential on the mix valve that you're using. We have 10-degree, 5-degree, and 27-degree, right?
We do not have a 5.
We don't have 5. We got a 10 and a 27.
We have a 10 and a 27, and all the different codes. And we have some 1017 valves. We have some 1070 valves. And I gotta straighten out the codes in my head on which one's which. So I get them all mixed up because there's way too many 1s, 0s, and 7s. That I get mixed up. Which one is 1017? Which one is 1070? And the delta and the differentials that you have in there as well.
Gotcha. Yeah. A question from Farad. Notice that none of the pipe is insulated. Welcome to the world of residential hydronics and plumbing. Yeah, that's commercially, all of that would be insulated by code, by requirement. Residentially, no, you're not gonna see it. It should be. You won't get an argument from me that it shouldn't, that it should be insulated. It won't be most of the cases, just because it's in residential, that heat stays in the house, more or less. Is it helpful? Is it wasted? But no, you make a good point. In it, that especially your domestic hot water piping, you insulate that thing, you're gonna get much better performance. It's just not done all that often, unless you got an inspector that's going to be a stickler. So that's the reason. Okay, I guess that's the reason.
So I'm going to bring back a question that came up earlier from Thomas, and he was asking. He's working on a baseboard heating project with townhouses. And he did the heat load on the project, and he's also done the domestic load on there. At each one is around 350,000 BTUs each. Do we add our BTUs together? Do you pick one to size the boiler? Do you fall in the middle? Right, so that conversation happens all the time on sizing your boiler. Mm-hmm. When you have a heating demand and a DHW demand. Which way do you go? Right. Do you add the two together? Do you split the difference? Do you go to the lower? So it's
now in residential applications, we include domestic hot water priority, because if the heat's off for 15 minutes, now no one's going to freak out, right? Because we're dealing with a small tank, it should recover pretty quickly, right? So in a residential application, it's why in our controls we have domestic hot water priority built in. But we also have the priority protection. So after 1 hour, it says, forget you, we're going back to heating the house because I don't know what's going on with the hot water. In a commercial application, a multi-residential application, that's a different question, right? Because how long is it going to take to recover, and how long can you go into priority? So I'm not, again, that's a control function I'm not quite as familiar with. I would think that's why a lot of times they'll have separate water heating boilers and separate boilers for that kind of applications. I would think doing priorities probably not the best idea, but I'll defer to other opinions on that.
Yeah, I would say, yeah, I think it will depend upon the storage that you have and the draw and also the stuff in there too for that project, like a 12-unit apartment here. Yeah. Yeah, and I honestly, yeah, just like you said, either separate water heaters altogether or separate boilers doing that, or twin them, rotate and stage the boilers. If you're going to put two in, you could still build one system to put two smaller boilers in. Make sure they can rotate and stage, so this way you only need one, for a majority of the time, between heating and DHW. Yeah.
Right. Yeah, Brad Paul says it depends a lot on the thermal mass of the emitter. Yeah, radiant's going to be different. If you got radiant heating, if you got air handlers, not so much. So again, goes back to my cousin Vinny, right? good butt kicking, $200. You got to make a decision. But I think, again, I think separation is probably, depend. The larger the project, I'd say the more separation is probably a good idea. Cool. All right. Well, anyway, we've pushed the old envelope. We understand the difference in valves. Let's just take a look at a couple of takeaways or takeaways.
I see what you did there.
Yeah,
I know.
I did that. First off, size the pipe to spec. All right. So again, if you're going to do that 141,000, 10 gallons a minute, size the pipe for that, right? Size the pipe for 10 gallons a minute. If you're doing the smaller boiler and you understand the differences in BTUs and flow rates and requirements, you size the pipe accordingly. Okay. You size the pipe accordingly. I'll tell a story now. I had I got from Bruce Marshall, the smartest man I've ever met. Bruce Marshall, the old trainer from Emerson Swan. What a great guy who is now retired. But he said he got a call from a contractor once who says, you know, what did you do to your product? It sucks now. He says, well, we didn't do anything to our product. He says, I don't know, something's wrong with the water, with the indirect. It sucks now. I've been doing all these things the same way. They've always worked. This one doesn't work. What's the problem? And well, you're in a different house, man. You made a copy of a copy of a copy of a copy of a copy, and you got away with it for a long time. But how similar is the hot water load in this house compared to the first one you did that you did the copies of? And he goes, oh, I didn't think about that. Yeah, it's different. So in this one, he needed a bigger, he was using 007s and 3/4 inch copper because the tapping on the indirect was 3/4. So why the hell would you run anything other than 3/4? Understand that the tapping on that heat exchanger going into the tank is just pressure loss. It's not a flow limiter. It's a pressure loss. The passageway through the heat emitter, through the heat exchanger is even smaller. All right, but you still got to get the flow rate through it. It's all pressure loss. So you got to run, if you got to run 1 inch, you got to run 1 inch. You got to run 1 1/4 inches, you got to run 1 1/4 inches. That's just the way it is. It doesn't matter what the size of the tapping is. You just push down or up or whatever. So the guy was doing the same thing over and over again, and he finally ran into trouble. That's what happens when you don't do the math. And most of the times you're going to be okay. This one time, you know, karma caught up with him. So size the pipe properly and then pick the right pump. And if it's a multi-speed pump, pick the right speed. Okay, pick the right speed. And then you size the tank capacity to the biggest dump load. Again, I've always been a believer, and maybe if anybody has any other opinions, please chime in. But I've always been a believer that your stored capacity should match the dump load. So if you got a big tank or if you got a big tub that you're going to want to fill, you should have usable capacity that matches the amount of gallons you got to put in that tank or put in that tub. So it's a 50 gallon, you need 50 gallons. You want to have 50 gallons worth of usable capacity in that in the tank for the 50 gallon tub. That's just the way it is. Even though, yes, you're going to be tempering down, just be on the safe side, because when you want to use a 2-person tub, you really want to use a 2-person tub. And then just watch your fixture flow rates. That's going to be the other important part. Is that good? Okay, and our formulas, I'll leave these up if you want to take a screenshot of them or whatever. Tank capacity times 0.75, that gives you your usable capacity or your dump load, if you will. Recovery is boiler output divided by 45,000, we'll call it. That just keeps it simple. But 8.33 times 60 times 90 is technically correct, but 45,000 is close enough. We're not flying this thing to Mars. We're just making hot water, right? Usable capacity plus recovery equals first hour rating. And then T mix minus T inc divided by T stored minus T inc. That's your storage factor. That's part 1 of the tempering valve equation. And here's part 2 of the tempering valve equation isn't written down. It's a usable capacity divided by storage factor gives you your tempered capacity. A usable capacity divided by storage factor gives you your tempered capacity. So that's indirect piping, pumping, and sizing in a nutshell. I hope this was useful for you. I hope this was helpful. Let me know. Give me some feedback. Was this new information, useful information for you? Is this kind of helpful? Could you see using this tomorrow? I guess is the kind of the question. Is this something you can use tomorrow when you're doing your job? Because if there's a yes, then we've done our job. If it's a no, well, we got to sit down and rethink this. So, and I'm just going to think about a tub like that. I think that would be really cool to have. So, guys, what do you say? Anything we got to catch up on here in terms of questions or comments?
So Steve was just telling me that 1017 valves are for your tank master valves, and 1070 is used for your point of use. He was just trying, so where do you use the different standards on the mixing valves that I was bringing up before?
Very good, very good. Excellent, excellent. So
I'm trying to troubleshoot something with Rob Kaplan's house.
oh, okay, there you go.
It seems like his tank turns on, calls for heat 3 to 4 times a day.
Well, that's interesting.
Yeah. So, I mean, if you're losing a half a degree an hour, it should go. And if most of your aquastats have a 9-degree delta, so it should sit there for, what is that, half a degree, 18 hours?
Yeah.
Right.
One would think.
So, interesting. That's why I was curious. I was asking them what type, standard. It's a standard indirect tank, so I'm really surprised by seeing that, how many times that kicks on and off. My house kicks on and off a couple times a day, but I also have a reverse indirect, so to speak. I've got boiler water in a jacket with DHW in a coil, so it cools off much faster in that respect.
Yeah, I mean that might be an aquastat issue. It's if no one's using the hot. I mean, if you're using a lot of hot water, then yeah, it'll turn on and off.
Well, yeah.
If it's just sitting there and nothing's happening on, that's something's weird. That's a little bizarre. You'd want to know what the aquastat's doing, what it's set for, what's causing the temperature to drop in the tank. What's causing that boiler. The boiler's firing for a reason, right? There's got to be a reason that's making this thing kick on. So you'd want to know what it is.
Obviously, the higher the temperature stored, yes, the higher the delta T between the tank temperature and the surroundings. You might see a little bit more kicking on and off that way too, but it seems like 3 to 4 is a lot. Yeah. So he's storing, 140 mixed down. Yeah. New aquastat installed.
I see a comment here from Steve St. Hilaire. I've done studies on the gas usage of indirect water heaters versus gas-fired. Indirects use 5 to 10 times more fuel. I think it's attributed to the heat transfer efficiency of the coil. Let's ignore standby loss. How efficient is the coil at transferring the heat from the boiler to the potable water? Again, to me, it depends on the BTUs and the flow rate, but some are better than others. I'm sure some are better than others. I got to tell you, this is my own personal opinion and our personal experience. My old house in Minnesota, I had a condensing boiler, and and my domestic hot water was made through a heat exchanger, so a little flat plate heat exchanger in the system. So it was almost like a instantaneous or tankless water heater basically. So it only made domestic hot water when I was using domestic hot water. And in Minnesota, 2 adults, 3 kids, all teenagers, we were averaging about $20 a month for gas in that respect. So that's a little bit different. I'm not keeping 40 gallons or 60 gallons of water up to temperature. Okay. That might be the difference. There was that part of it right there. But again, it's essentially an indirect, more or less. So
I would say when you start looking at indirects, there are also indirect efficiencies. Or different ways in how they transfer the energy. And what you really want to look for is also surface area. What is the surface area of the coil itself inside the tank? Which means, does it have 10 turns? Does it have 20 turns? Right? So if the more turns you have on the inside of that tank, just means there's more surface area to transfer that energy through. So that is also something else. So yeah, not all indirects are the same. Obviously, right?
Water quality plays a role here too, because some have ribbed. The coil is made of ribbed pipe, and if you got hard water that's not treated, well, that hardness is going to cake on that sucker pretty darn quick, and that's going to impede your heat transfer. That's just reality. The same thing for anything with a stainless steel heat exchanger. Sometimes they have to expand and cake that, crack that stuff off. There are a lot of off the books solutions for that we really can't talk about, but indirect people will say you go do this and that'll blast all that stuff off and you'll be fine. But they they don't write it down because it's kind of dangerous. But those also play roles, okay? And that plays a role in a tank type water heater as well, just like a gas fired water heater. The more crap that collects on the bottom of that tank that you don't flush it out very often, well, all that heat has to go through that crap at the bottom of the tank before it gets to the water. That's going to impact things. You know, your flue gases you're going to lose flue gases. You got all kinds, you know, heat loss with flue gases. There's all kinds of different things going on with that. And the crap at the bottom of the tank, that's what causes the tank to fail, you know, because you get so much heat. So we don't have, when we develop that perfect water heating solution, by golly, we'll all be rich. You know, there's always just said, there's trade-offs to everything. Trade-offs to everything. Question: what should the temperature difference be across a heat exchanger? In an indirect, they're typically sized to a 30-degree delta T. So when you're sizing, you're getting for your flow rate, et cetera, it's usually designed around a 30-degree delta T. Is fouling more of an issue with indirects? Not really. It's an issue. It can be. It depends on the heat exchanger and who makes it. It can be. I don't say it's more of an issue than with a tank type water heater, you know, with a direct fired water heater, or even a tankless. I don't think it's more of an issue. It's just a different set of issues. Everything's a trade-off, man. Everything is a trade-off.
Right. And so Robert's saying also, is a larger delta T better? Well, the larger it is, but then you start getting to your close approach to what temperature you want to store, to what your boiler temperature is. And then heat transfer is not happening. So you'll get more stratification in the tank with the coil, stuff like that. So that's what they're also looking at too, that inrush of 50-degree, 60-degree water into the tank, the coil temperature. So all those factors come into play, which is interesting. So maybe it is a conversation with the tank manufacturer there, you know, making sure all the settings are just right, you know, if you seem to be kicking on and off. And I guess it could also depend upon age, you know, if that insulation ever gets wet too. You may not know you got a leak because it evaporates. And if that insulation gets wet, you've got a little bit more of a transfer happening too at the same time. So, yep, excellent.
Yeah, and again, when you have the thing about heat transfer is funny. If you got a closed loop, if I design to a 10-degree delta T, I'm only getting so many BTUs, right? The BTUs are the BTUs. I'm not getting more, right? My recovery is my recovery because of the BTUs. It's just a matter of how long the boiler runs and how long we can sustain it. You know, it's just the way it's going to be. Smaller delta T, higher average water temperature, lower delta T, wider average water temperature, and smaller pipe, smaller pump. I mean, did I say this already? It's all a trade-off.
Yep.
All righty. You do get more BTUs with a higher delta T because of increased combustion efficiency. You don't get more BTUs, you get more combustion efficiency. You get a more efficient burn. It lasts longer. A boiler that's capable of making 75,000 BTUs is a boiler capable of making 75,000 BTUs. I don't think there's a whole lot of, if we can argue about that, we can argue about anything. And I know in our world, we can argue about anything, but that's a tough one to argue about. It's just, in what manner do we swap those BTUs out, and how quickly, and what is the impact of doing it fast versus doing it a little bit slower?
Right. I guess you're not going to get more BTUs out of it, but would you have a larger delta T with a mod-con boiler, meaning you're sending back cooler, the boiler becomes more efficient. Yeah, so much happier. Sure that you do the second part of the mod-con boiler, meaning the con part. We want to condense. So if the water temperature coming back to the water heater or to the boiler is below 135 degrees, yes, you're going to start condensing. But here's also the interesting part. What is the boiler doing at that point? Making hot water, all right? And at that point is when you don't want to really start playing around with too much efficiency if you start running out of hot water, if you start increasing the delta T, right? So you want to make sure you got hot water, you want to make sure you got it, right? So that's the demand, it's hot water. DHW demand, as we call it, right? We demand hot water.
I know in my 6-person shower, I don't want 5 unhappy people. That's all I'm telling you.
I prefer the term car wash shower.
There you go. That's a little bit more appropriate term.
Yes.
Okay. Using a mod con with an 80-gallon tank. Oh, hold on. I can't see. Let's get these specs on.
I've been able to run my supply to indirect at 135 with a return always in the condensing mode, never run out of hot water.
There you go.
Gallon. Yeah, that's a big old tank, definitely.
Yep. Yeah, again, trade-offs. Wider delta T, that lower water temperatures, bigger tank. That's one of the things with air to water heat pumps and using an air to water heat pump to make your domestic hot water with an indirect tank. Bigger tank, gotta have a bigger tank, right? Because you only get X amount of hot water. The temperature of the water coming from that air to water heat pump is limited. So yeah, you want to make the most out of it. You're gonna have to have a bigger tank, man, much bigger tank.
Yep.
So trade-offs. Did I say that already?
My indirect tank is 23 gallons. 23. Yeah. But
that's a little.
Yeah, run out here. Yeah.
Yeah. There you go. There you go. And you don't tell your mother-in-law anything, and she runs out of hot water, and because you're insensitive.
That's right. That's right.
Can you estimate recovery rate of any indirect tank with that 90-degree DOE delta equation? Yes, you can estimate, absolutely, because it's all about the BTUs. Okay, it's all about the BTUs. I can't recover any more than this. Any variations in numbers are going to be specific to that particular hot water tank. That's why they all publish their own numbers. So you can see the way we did it, we had 212, we had 214. Superstore had 212 printed, so it was a little bit of a difference. So yeah, you can, because that's just going to tell you what's possible with the BTUs you have available. The indirect's going to be they all size these things and they all size these things at the same math anyway. So you'll get a pretty good idea. So yes, I would say that is you can do that, channel. Excellent. Right. This has been great. I love the questions, man. I absolutely love the questions, folks. Thank you so much for the gift of your time today. I love spending time with people who are passionate about indirect water heaters. You got to understand, you go out in the regular world and start talking to people about indirect water heaters and getting into this stuff, they generally don't like you. Okay. I mean, I try having this conversation with my friends who are not in the industry, and they really said, I think it's time for you to go home. You're starting to lose it. Having this conversation with people who dig this stuff is really a lot of fun. All right. I think that's why we do what we do, right? There's only one way to scratch that itch, and that's talk to people who get it, right?
Yep. So again, before we hang up.
Oh, well, big announcement, Dave. Take it away. Big announcement.
So 23 hours time, you'll get an email with a link to this recording, and you'll get your certificate of attendance for your PDHs as well. So look for that email. But also tomorrow night, 7 p.m. Takeaway live. All right. So we do so similar to this, but a little bit different. So we still use this platform, but we are also streaming on Facebook, LinkedIn, and YouTube at the same time. So make sure you follow one of those accounts from Taco, and log in for Takeaway After Dark tomorrow night, because we do have Cheryl Merchant, our president and
CEO.
Yep, sorry, was going somewhere else for a second. Will be joining us as well. So take a look at some of the socials, because we also she's not just joining us, but she's also welcoming questions from you out there. And if you take a look at the socials that are out there, take a look and submit your questions beforehand so we can make sure we get to them. We've got a ton of them already. So if you've got something that's really pressing that you really want to discuss with Cheryl and the future of Taco and where we're going, please do. So take a look at that, try to get it out to us beforehand so we can organize them and have them all prepared, ready to rock and roll. So that's going to be tomorrow night, 7 p.m. Eastern.
It's going to be a very big deal. How many times do you get the opportunity to talk to the CEO, directly to the CEO of anybody, any company in this industry? That's
in any industry, really.
In any industry. And Cheryl is engaging, and she's fearless. So she'll, you come up with any question regarding the operations and future of Taco, and she'll embrace it wholeheartedly and give you a real thoughtful answer. Anything you can say great about the training department specifically, if you are on live with us, we would appreciate. But yes, Mark Amaro says, yes, she is a rock star. Absolutely. Absolutely. So we encourage you to join us Facebook Live, LinkedIn Live, YouTube Live, or directly through GoToWebinar. Please join us tomorrow. Tell all your friends. Tell everyone you know. We'd absolutely love to have as many people on as we can, and that'll rock and roll. All righty.
Yep.
Cool. Well,
See
thank you
guys
all
tomorrow
again.
night.
See you all tomorrow night. Thank you for the gift of your time. We just so much appreciate this. You're joining us and allowing us to share this stuff with you. So it means an awful lot to us. So thank you all. And we will see you tomorrow night.
Tomorrow.
Yeah.
Later.
Bye-bye.